In this video we're going to talk about electric fields. Electric fields and electric potential and electric potential energy. And we are still on topic 10 of the IBDP syllabus, which is a higher level topic. So let's take a new slide. So let's remind ourselves what we mean by an electric field. So if we have a negative charge and we put a small positive test charge in its vicinity, then there will be an attractive force between it and it will be pulled into the negative charge. And there are, so now we're talking about electric fields. You can think of the field lines as the direction in which the force would act on if you put a small positive test charge somewhere within the vicinity of another charge. And they have a direction and a magnitude, and they act, in this case, towards the center of the negative charge. These are radial field lines. So, electric field strength is equal to E, which is the force a positive test charge would experience per unit charge. And don't forget, it is a vector quantity. And since we know that the electric force is equal to little k, big Q, which is the charge on in this case, the negative charge that's pulling in, big Q, little q divided by r squared, then E, and it's a vector quantity, sometimes you'll see this little symbol for the vector, E is equal to k, big Q, little q over r squared divided by r. So one of these r's cancels, and you get E equals k q, little q over r. Let's take a new slide. So if we have two or more charges, then we have to work out the vector sum in order to find the resultant electric field. So let's take the example of a E field due to a dipole. Now what is a dipole? Well, a dipole is two equal and opposite charges. Here we go, I've got one charge here, plus Q, and I've got another charge here, negative Q. This is the dipole, and they're separated by a distance A, and some distance away, there's a point here, P, and It just so happens that P is equidistant from negative Q and Q. We can define this distance here as R, and this distance here as also R. And the perpendicular distance from the centres of the two of these charges to P we can define as D. It just so happens that this distance here, R, is at an angle theta to D. So what's the resultant electric field strength due to these two charges? Well, if we were to put a positive test charge here, then the positive test charge will be pulled into this negative charge here. So, and the force would act along this line here. Therefore, the electric field strength due to negative Q would be this component here. Now, if a positive test charge was put here, then it would feel a force pushing away from positive Q along here. So this would be the electric field strength due to a positive test charge plus Q. Now, if we think, if these charges were equal and opposite, then when we break these two fields' strengths down to their components, the horizontal components would exactly cancel, and we'd end up with only the components vertically downwards giving the total electric field strength. So that's what we're going to find out. It's the resultant, if just looking at the force vectors, the resultant is going to be pointing directly downwards. Question is, how big is that? So we're going to try and define that quickly. It's going to be a bit of maths here, just try and stay with me. So for one of the electric field strengths, let's take E negative Q, just talking about the magnitudes now of E negative Q. That is going to be K times the charge on this charge, which is Q, divided by R squared, the distance the charge is apart from point P. If we look at this diagram now, we have a little right angled triangle here whose hypotenuse is R squared. This length here is A upon 2. Sorry, the hypotenuse is R, not R squared. And the base here is D. So from Pythagoras, I've got R squared is equal to A squared upon 4, A upon 2 all squared, plus D squared. And if I square root, I get R is equal to A squared upon 4 plus D squared square rooted, which is the power to the power a half. Now this angle here is theta, and I want to find, we've worked out, we said that the horizontal components would exactly cancel, so we want to find the this component of the electric field strength pointing downwards, and that is going to be equal to the sine theta component of the electric field strength due to negative Q. And it works out that E sine theta, here we have theta, is going to be equal to the opposite side of this triangle, A upon 2, divided by the hypotenuse, which is R. So E sine theta is A upon 2R. So the vertical component of the electric field strength due to negative Q is equal to sine of theta of KQ over R squared. So we get K times, or rather let's substitute in for E sine of theta, which is All of this is times by E, by the way. A upon 2 lots of, and then instead of R, we're going to put this expression here. A squared upon 4 plus D to the power half, multiplied by Q, KQ divided by A squared upon 4 plus D all squared. And when we simplify this, we get K, take the K out the front, times by A times by Q divided by 2 lots of, and then these two things multiplied together give A squared upon 4 plus D squared, that should be there, to the power of 2 multiplied by something to the power half is to the power, sorry, this should be a 1 here. Something to the power 1 multiplied by something to the power half is something to the power 3/2. And the total, the resultant here, is going to be twice this, because this is only due to one of the charges. So the total electric field strength due to the dipole is going to be K times AQ over A squared upon 4 plus D squared to the power 3/2. This is probably one of the more challenging problems you could be given in the exam, involving addition of vectors and sine thetas of things, but now at least you've seen it. So let's carry on in this video and talk about electric potential and electric potential energy. Take a new slide. Electric potential and electric potential energy. So, and it's analogous to what we've talked about in a previous video, the gravitational potential and gravitational potential energy. Writing in short form here. So the difference here, though, is we can have different signs of the gravitational potential energy. So imagine we have a charge over here, Q, and we bring, here we have a small positive test charge plus Q. Now the question is here, what's the direction of the force that plus Q is going to experience? Well, out here at infinity, it's not going to experience any force, theoretically. But if we bring this positive test charge into the vicinity of big Q, then the force will be repulsive. This is a positive charge, this is a positive charge, so there will be a force pushing it back. And we can define the distance that the small test charge plus Q is from this point as being little r. And it turns out that the electric potential is the work done. We have to do work on the charge to bring it into to this position. The work done in bringing a small positive test charge from infinity to a distance r from charge Q. And it's given the symbol V subscript E, and it equals the work done per unit charge. Per unit charge, I forgot to add that here. Can you guess the units? Well, work is in joules, and charge is in coulombs, so it's joules per coulomb. And important to note here that it is a scalar quantity. So when we add up electric potentials, we just have to add the numbers rather than add the vectors. Let's take a new slide and talk about electric potential energy. Well, electric potential energy is given the symbol EP, and it's simply equal to the charge multiplied by the electric potential. So the electric potential energy at some point P in an electric field which has some electric potential is defined as this. Now, in order to find out the work done, W, in bringing so say now we have a charge here Q, and we bring a positive test charge from a point B, regardless of path, to another point A, then the work done is equal to the charge times the change in electric potential. Because using calculus, by integrating the force from infinity to R, we find that actually the work done in bringing a positive test charge from infinity to R is equal to K times big Q little q over R, not R squared. So here we have to work out the difference between the electric potential at B and the electric potential at A. So this would be Q, lots of, where we have a constant charge, lots of the electric potential at B minus the electric potential at A. And remember, electric potential is a scalar, so you just need to add up the individual contributions. Lastly, in this video, we're going to talk about the electric potential for a charge on a sphere. Right now we've been talking about point charges, but what's the difference if you have a charge on a sphere? Let's have a new slide. On a charged sphere. So here I have my charged sphere, and there's charge on the outside of the sphere worth. So the charge on sphere here is big Q. Well, it actually turns out that in this case we have a positive charge here. That if I have a graph of underneath here, and we define the radius of the sphere to be capital R, and this graph down here is going to be electric potential against distance from the center of the charged sphere, then it actually turns out that inside the sphere we define the electric potential to be a constant. As soon as you get it outside the sphere, then it becomes proportional to 1 upon r squared and starts to decrease like this. So inside the sphere, the electric potential is equal to K big Q over big R. It's a constant. Whereas outside the sphere, for example, at some distance here, R from the center of the sphere, then the electric potential equals K big Q over little r, and it has this inverse proportionality. Likewise, if we have a negatively charged sphere, let's see how that graph would look. Do some fiddling here to put a negative sign there. Then we would end up with instead of a positive potential, we'd end up with a, so this would be 0 here, this is in the negative potential down here. We'd end up with a potential curve which would look like this. It would be in the negative values down here, and it would increase like this. So inside the sphere, for a negatively charged sphere, the electric potential would be constant and minus K big Q over R, whereas outside the sphere it would be negative K Q over little r.